In today's lesson, we're going to analyze graphs of polynomial functions. In our first example, we're going to identify the x-intercepts of the graph of f of x equals negative x minus 2x minus 1 squared. And really, this is very easy because this is practically in factored form. I can simply rewrite this as f of x is equal to negative x plus 2, and then x minus 1 times x minus 1. As I can see here, I'm going to have a double root here because I have two factors that are the same. So remember, we can just set these equal to 0, and we can find what our factors are going to be using the zero product property. So I'm not really going to go through that process because it's one that we're familiar with. So therefore, our x values in this case are going to be negative 2 and positive 1. But we want to write these as x-intercepts, which are points. So I'll have a x, well, this will be negative 2, 0, and positive 1, 0. And since this one here is going to be a double root because there's two of them. So that's where you're going to get a little, either a local minimum or maximum just touching the x-intercept. So the turning points of a polynomial function can be determined based off of the degree. The graph of every polynomial function of degree n has key phrase, at most n minus 1 turning points. So if you have a degree of 3, then there's going to be at most 2 turning points. Or if you have a degree of 4, there'll be at most 3 turning points. So the number of turns in a graph is always 1 less than the degree, is what it's saying. And likewise, if a polynomial function has n distinct real zeros, then its graph has exactly n minus 1 turning points. So as we talked about in the last section, the degree tells us how many real zeros we could have, and then we can determine the number of turning points because there's always going to be 1 less than that. So in our second example, we're going to graph h of x equals 0.5x cubed plus x squared minus x plus 2. When we graph, we want to identify the intercepts as well as any local minimums, maximums, and end behavior. But we'll utilize a graphing calculator to help us when determining this. So I'll go ahead and pull mine out. But before I do, let's see if we can predict how many turning points there will be in this graph. I can see that this function has a degree of 3, so at most it should have 1 less, or 2 turning points. So let's take a look at our graph. So I've already gone ahead and entered in the equation. And looking at the graph, I can see that we have indeed 2 turning points here and down there. So when I graph this on paper, I'm going to be looking for the x-intercepts, local maximums and minimums, as well as end behavior. So let's start off with the x-intercepts. So I'm going to go to second calc, and another name for the x-intercept would be 0. And I'm going to go to the left of that point. So I'm going to set my left boundary. And now I'm going to go to the right of it just a little bit and set my right boundary. and then I'll press enter, and it looks like it's about negative 3.1. So I'll jot that down as my x-intercept is located at negative 3.10. I want you to go ahead, when you write this down, round to the nearest tenth. That would be awesome. Okay, next we only have 1, 0, so let's go ahead and get our turning points. We have one local maximum, so we'll just have to find one here. So that's going to be a maximum. That would have been option 4. So I'm going to go to the left of it, set my left boundary, then I'm going to go to the right of it, set my right boundary, and then just press enter. And this one is located at negative 1.7 and positive 4.1. So let me go ahead and make note of that. And now I'm going to find my local minimum. So we'll go under second calc, but this time we're going to select option 3. And we'll go set our left boundary on this guy and press enter. That went a little bit too far. I'm going to backtrack just a bit. And then my right boundary. Alright, that should be good. And that's about 3.9 and 1.8. Okay, so we have the x-intercepts, local maximum and local minimum. And now we'll just plot these points. So let's see here, negative 3.1. So that's just going to be just a shade to the left of negative 3. I'll put that about here. And the local max at negative 1.7, so just short of negative 2, just to the right of that. And then 4.1, 1, 2, 3, 4, so just a shade above 4. So that looks like a good point. And local minimum would be 0.39, so a little bit left of 0.5, and then 1.8, so that'll just be a little bit below 2. Okay. And then we can use a table to fill out other points, but you know how to do that. So I'm not going to illustrate that here, but you would fill out any other integers in between those. And then I'm just going to connect my points as best as I can. Like so. Okay. And let's not forget our end behavior. So here we'll say h of x is approaching negative infinity as x approaches negative infinity. And the right end behavior, h of x approaches positive infinity, or infinity, as x approaches infinity. So there we have our graph, and we know how to analyze polynomials based off their equations a little bit more. So that's it, and I'll see you on the flip side.